So I start the recording now. Yeah, somehow. Okay. Yeah, thanks for reminding. Okay, good. So we continue. So when we add with quadratic, right, there's some chance that there is some slot, right, cannot be visited. Okay. Because when we add something, right, we don't know, right, because the number maybe will be step, right, and there's some slot will be never visited. Okay. So normally, right, people will choose the h is the two power of something like 2 power n, and the C1 and C2 usually 0.5. Okay. So this is the, I mean, in mathematical field, people already proved that using that one, right? Normally you have the very good distribution of the propping. Okay. So, okay, this one is, I give one illustration for you to see. For example, we have the hash table size is 8. Okay, we have so 8. Okay. They want to add the key into. Okay. So yeah, the key we want to add 4, 13, 19, and 11. Okay. So we start with 4 first. This one is just like, I mean, for the easier calculation, so that because later we add this portion into the key, right? So we just recalculate it. Yeah, we just recalculate so that later we can apply directly. I mean, easier to observe. Okay, just recalculate the value. Okay, anyway, we start with the key 4 first. 4, then modulo with 8 is 4, right? And 4 empty, so we just put a 4 here. There's no collision. Then we continue with 13. 13 modulo with 8 is 5, right? So we put 13 here. Okay. 19. 19 modulo with 8 is 3, right? So we put the 19 here. Okay. Then 11. 11 modulo with 8 is 3. Then the collision happened, right? So for the linear things, you remember, right? If the collision happened, then we find the next one. Empty or not, we find the next one. Empty or not, then we find the next one. Yeah. But for it, the quadratic, right? We don't add 1. We add this amount. Okay. So for example, we start with I equal 1. I equal 1, we already calculate I equal 1, then this one become 1. So it means that we add 1, right? We add 1, it becomes 12. 12 modulo with A 4, they occupy. So we cannot. So we start with I equal 2. I equal 2, this one value is 3. This means that we add 3 to 11. So it becomes 14. 14 modulo with A is 6, right? And it's empty. So we put 11 here. Okay. So you can see, right? Actually, this one we don't sequentially travel on the slot, right? But we do the step by the quadratic function. Okay. So next one you already move to here. Then you put 11 here. Okay. So this one for the secondary clustering, right? Dimension. This one solve the problem with the linear propping, because the linear propping, right? Because you sequential search, right? Then somehow you can make all the key close to each other. But this one, because the step is quadratic, right? So it may go, I mean, go around the table easily, right? It's not the sequential one. It means that in the I mean the hash table, right? After you add the hash key, right? So maybe you can see that the distribution is quite good. Like some key will be maybe here, some key, the distribution of the cluster also good. It's not like the linear propping. Linear propping on the key may tend to close each other. But for the quadratic propping, you can see that even though if there's the cluster will be distributed. Okay. Because we not add the linear thing, we add the quadratic things. Okay. So if you have time, you can insert k equal to 3 in this example, you can see. Okay. Another way for the probing is double hashing. Double hashing is you just, I mean, instead of just one hash, right, you do two hash. It means that you multiply every time the I with the another hash function. Okay, yeah. So for example, you have the hash table with a modulo 7, right? And we define the probing is just k plus I times dk, and dk is another hashing function. It's just a modulo 3 plus 1. Okay. So now we see how we add the key into the hash table. So we start with 0, of course 0 modulo with 7, right? Then no collision, right? So we put 0 here. Then 4 modulo with 7 is 4. So we put 4 here. Okay. Then 13 modulo with 7 is 6, right? So we put the 13 here, no collision. Okay. 19 modulo with 7 is 5, right? So we put the 19 here. 11 modulo with 7 is 4, right? 4, now we have the collision. Then how we do that? We just add I times dk, right? I start with 1 first. dk we see k now is 11, right? So the dk will be equal, d11 will be equal 2, right? So this one equal 2, right? 11 modulo with 3 plus 1 equal 2. Or 3, right? 3, sorry. 11 modulo with 3 is 2, add 1 is 3, okay? So it means that we add with 1 times 3, right? So it means that we add 4, right? So we add 1 times 3, it means that we add 3, sorry. So we add 3 into. Add 3, they become 14. 14 modulo with 7 is still collides, right? Okay. Then we increase the I into 2, become 2. So become 11 times plus 2 times 3. So it means yeah, 17. Okay, I will back to the secondary cluster later. Okay. So now we here we have the 11 plus 6 modulo 7 is 3. So we can put 11 here. Okay. Yep. So they're still asking about the secondary cluster. Secondary cluster. Secondary cluster here. So what the secondary secondary cluster? For the, you remember for the primary cluster in the linear probing, right? So the primary cluster happen because when you insert a few key, right? It's already here. Then there's the new key, right? It have the a high chance, right? It will hash into some hash table here. And then how you add it? You add one more, right? After you searching, you add one more next to the cluster. It means that you will increase the cluster bigger and bigger, right? High chance that the cluster will be bigger and bigger. And in some cases, right, when you add, right, you can see there's a very, very big cluster in the hash table, while all the area empty. Okay? It's just because the way we add, right, we sequential search and we just find the next empty one. So we make the cluster bigger and bigger. So that they call it primary cluster. So what is the secondary cluster? Secondary cluster, because when we have the collision, right? We don't, for example, we have a cluster, right? And if the new key happen in this cluster, right? We don't search sequential search, but we add with some quadratic amount, right? And quadratic amount will help you to move this one into the new one, very far away, maybe far away from the original cluster. Then you may go to another one. So you don't make the original cluster bigger, but you for another cluster. So they call it a secondary cluster. So in this way, right, maybe because you add the quadratic amount, so that's why you make the distribution of the cluster will be quite evenly. It means that the distribution nicer than the linear probing. Linear probing, the tendency is you only have one primary cluster. Normally you have very big primary cluster, right? But for the quadratic, you may have the cluster, but the cluster maybe you have many cluster and you don't have a very big one. The cluster quite distributed. To understand? So that's how they call the secondary clustering. Yeah. Okay, good. So we continue. So this is the three way for the hashing. For three way to do the probing if we have the collision in the open address. So in summary, right? This is the time complexity for the probing. This one is, I mean, how to prove it is quite complicated. So you can find it. If you are interested, you can find it here. But in summary, right, you can see that it is just a function of 1 divided 1 minus alpha, right? It's a function of this. Yeah, you can see for linear probing or the double hashing or something. So it's all about the function of 1 divided by 1 minus alpha. And again, I mentioned, right, if we choose the alpha carefully, like the alpha is proportional to the hash size, right? So the alpha will be the constant. For example, we choose the alpha is like 1/3 or something. So alpha will be constant. Therefore, the search time also will be constant. It will be like the O1. Yeah. The search time still O1. Okay. So I mean that's the the time complexity for the probing is still O1 if we choose the alpha is like constant value. Okay. Now there's a problem for the open addressing. For example, you remember for the linear probing, right? When you add the key, right? For example, you add a key after you do the hash function, right? The key have the similar value with the key already occupied. So I showed it X is occupied position, right? So after you do the hash function, if it hash into the occupied position, then it will find the next one, and you find the next one, and you find the next one, and the next one, for example, the A, right? The key A. The next one is not occupied, then we just put the A here, right? Then how you do the searching later? The searching later, you also do the same thing, right? You do the hash function A, apply to A, then you go to this one, right? And you check whether the key is A or not. If not the key, then you continue. And this one you also see occupied. It means that previously, right, when we add, right, they are also occupied, so we need to continue, right? It means that when you search, right, if the collision happen, you can see that the same hash value, but the key value is different. Then you just continue, right? Continue until you find the key A, or you cannot find the key A, right? You cannot find the key A. There maybe B, C, D, or something. Then the next one is empty. So it means that there is no key A before, right? So it means that for the open address, right, we do the hashing, then have the hash value, right? We go to the entry. We do the, for example, if for the linear search, we do the sequential checking. If the next one is still occupied, then you check the next one until we can find the A, or until we find the next one is empty, right? Empty means that there is no A, no key A, right? Then we stop. Then we return that, okay, we cannot find key A. A is not added before, okay? So the stopping area is either you can find A or you find the next one. The next dropping is empty, okay? But the problem is how you define, how you delete a key. For example, you have the A hash here, and then this one is B, C, D, E, F, right? Then how you delete? For example, you delete a D. Okay. For example, yeah, for the pseudocode I will give in the lab. So for the hashing, no worry, we will give in the lab, in the template, the pseudocode. Okay. So for example, previously you add A here, right? So A coming here. Now, if you want to delete D, okay? If you delete D, right? If you erase the D, totally erase it. So you make this slot empty, right? Then later, how you find A? A will be, yeah, the teaching assistant will go going through the lab, or they can give you the solution also. Okay, or I can send you the solution also at the end of the lab. Okay? You can practice it during the lab. So for example, you delete the D here. Okay, totally delete. Yeah, so that's the way I said. Yeah, so I will upload the solution, so no worry about that. So if we totally delete the key here, right? Then later, how we search A? When we do the hashing, right, the A will become here. Then we, the F, right, it's not A, so we continue E. E not A, so we continue. Then we found that this one is empty. Then we stop, right? We didn't know it empty because it was deleted. They an entry before, but it was deleted. We didn't know about that. Then we see empty. We think that okay, it stopped already. Then we return okay, A not found, but actually A here, right? So for the open addressing, if you delete the key totally, right, then later when you search it, you have some problem because you see some empty slot here. Then you think that, oh, yeah, I already stopped the propping. Then you return no to A. But actually A here. It's because the entry D previously, but because D deleted. So therefore to delete a key, right, we don't delete the key. We just leave the delete key in the table. We still keep the D here. But we just do a marker indicate that it's not, they already deleted some marker something. Some marker like some marker some value something. So that okay, they're already the key value D, but this one already deleted. So later when you search the A, right, you still see this is the not the empty one. So you still continue until you find the A. Okay. So just notice about that. We don't delete the key. We just leave the key in the table. But we have one marker to indicate that this entry already deleted, but the key value is still there. So that later you can search. Okay. So therefore, and later if you have you want to add the new entry with the key D, then you just insert to this slot, and you remove the mark. You add with the new entry. Yeah. Okay. So because of the deleting, but still leave the key, blah blah something. So we may need the garbage collection to clean on the garbage things, right? To just improve the search time. Okay. Because sometimes we don't delete it, we just leave it, and then we add it later. Then there is some redundant things. Yeah, I just mentioned we don't delete it because if we delete it, right? So this position, the D position, right, become empty. So now it become empty, right? Empty when, and then later when you search, A's, right? Because the hash value of A will go here. Then you search A, you find, oh, this is not A, it's F. Then you continue the next one, like the linear one, right? Do the propping. So you search the next one, E, it's not A. Then you search the next one. That's what empty. Empty, then you think that, okay, this is the end of the propping. Then you stop. but actually the A here, A here, but because you they are already empty. Yeah. The marker is just some value because in the entry you have the key, right? You have the ID, right? And then some information here, right? Then you can information is just you can put some value. Yeah. Yeah. You can put some value, just a key, like one more integer number, like delete or not, like the d equal 1. You set d equal 1 is delete. Yeah. Just one more field. Yeah. In the data. Yeah. The placeholder or whatever. Yeah. Okay. Whatever the marker you can just put I mean the flag or something. Okay. Yeah, I just mentioned like if you will put it with the null, right? The null, right? Then it will have the problem with searching. Yeah. The search will stop. Yeah. Okay. Then this one for the open address, right? I mentioned right the number of the key because you store the key directly into the table, right? So the number of the key cannot bigger than the number the hash size, right? So if the key is just continue coming, right? Then the number of the key will be more than the hash table size. Then you need to do the rehashing. So rehashing very simple. Rehashing very simple. You just increase the table size, and then you need to rehash on the key. Okay. Okay. Can we do it? Given a now we cross the search. Can we do a try and catch? How can we know we continue? Because if you just continue, then you will search for the whole table, right? If you see the null value, but you still continue searching, then you will search the whole table, right? They're very inefficient. Yeah. So the null value mean that the null value mean that the probing is finished already. So that's why when you see the null, you stop the searching because you know that the probing already finished. Yeah. If you see the null, you continue searching, then it means that you search the whole hash table. Yeah. Okay. So yeah, for the summary of the hash table. So we know the close address hashing the average complexity O alpha, right? And for open address hashing the complexity OF of the 1 divided by 1 minus alpha. But if we choose the alpha is constant, then both of them is just the O1, right? Because they are constant. Right? And we know how to delete a key and how to rehash this. Yeah. Okay. So they are on for the hash table. Okay. So this is the hash table. We have the lab. So in the lab, I will give you the whether we need the close or open. Frankly speaking, right, it depends on the application. But normally, if you have the small amount of the data, right, if just the small amount of the data, then the open address hashing. I mean, open address hashing. If you just have the static number of the, you know, the number of the elements, and it's not increasing, right? Then you should use the open address hashing because the search time for, even though they are both O1, right? But the open address hashing, the search time is instantly, right? Because one hash table is just one key. You don't need to traverse the linked list, right? Right. So if you know the number of the key at the beginning, so you should use the open address hashing. But if you don't know the number of the key, and in your application the key continue coming more and more, right? So I think you should use the closed address hashing, because if the key is continue coming, right, it's increasing over the time. If you design the open address hashing, even though it's faster to search, but because the size of the hashing is static, right, and the number of the key cannot be bigger than the hash size. So if the number of key bigger, then you need to rehash, right? Every time you need to rehash, and rehashing, you know, right? You need to rebuild the whole thing, so very costly. Yeah. Okay. So that's why I mean, usually we won't know the number of the data stored in it. It depends. You don't know the number, don't know exactly the number, but you can imagine, right? For example, if you store the number of the students in the school, right, then you can imagine that maybe it cannot be more than 100K, right? The number of the students in the school cannot more than 10,000K, for example. You can have the upper bound, right? But for example, if you store the number of the user in the world or something, it increasing maybe 100 million or billion or something, then you should use a closed address. But if you can actually make the upper bound of the key, then it's okay. The table, you mean the hash table? Hash table is just an array, right? Hash table is just an array. Yeah, it's just an array exactly. Yeah, it's just an array. So that's why the search time is constant. Array A, right? Then you want to search for the position, the hash value, you just put the hash value I, for example. Then it instantly, right? Yeah, array. So the accessing to the hash slot is instant. Okay. So where will the hash table, you should implement an array. If you implement it a linked list, then when you want to access the I element, you need to traverse the first to the I element. It's not now. It's not the O1 search. It becomes the ON, right? Because the linked list you need to traverse. Right? Will be the empty slot if we do the secondary clustering. Secondary clustering, we also do the same thing. We do the probing. This week we don't have the lab. Yeah, we have the lab next week. For the secondary clustering, we also do the same thing because we do the probing. We search using the probing function. Okay. Yeah, correct. If we have the infinite data, so we should use the closed address. No, we do the looping. We do the modulo, for example, modulo, then we do the looping. Right. If you search until the end, then you go back up, we are modulo. Right. The thing is modulo. Yeah. Okay. So we continue with another things we call the wrap data structure. To store the data through the open address, okay, the insertion time isn't going to be O1. It's still O1. It depends on the it's still O. It depends on the way we do the probing, but the probing is also the probing. It depends. For example, it depends. The probing is the function of the 1 divided by 1 minus alpha, like I mentioned here. Okay. So it depends on how you choose the alpha. Yeah, of course. Of course, insert into the hashing in the open address, it will be maybe slower. Maybe there's so many collisions happen. Yeah, I will upload the lab by today or tomorrow, so you can try earlier. So no worry. And I will also update solution for you. If we use array, it wouldn't cumbersome if we want to perform the insertion. Insertion is just insert into the table. So what is the cumbersome? Yeah. I'm not so sure what you mean by the insert. We insert directly into the hash table. So we just check whether this one is empty or not, then we add it directly. Congruent, even though they are random, right? But random methods mean that you choose at the beginning, right? So later you also use this number. I mean, random here is you choose random at the beginning of the when you design a hash table, you choose a random number, not a random number during the adding. This means that the number is predefined actually. Okay. It's not a random number at the inserting or something. It's random number at the beginning when you design a hash function. Okay. Okay. Anyway, yeah, I think we should go to the graph first. Okay. For the graph, so yeah, new data structure. So the graph, you know the graph, right? A graph is just the connection between the vertex and two vertex. Maybe they have the edge or not, right? So just a graph is just a connection of the vertex. So the graph will be contain two elements: the vertex and the edge. The vertex, the set of the vertex and the set of the edges. Okay. So V is the set of the vertices, and the absolute V is the number of the vertices. Okay. And H E is the set of the edges or the link connect the vertices, right? And yeah, and we know, right, for the end for the V V vertex, right? So the maximum number of the connection will be V times V minus 1 divided by 2, right? Because the maximum means that we one not connect to on the order V minus 1 not. Okay. So the number of the edges will be range from 0 to V times V minus 1 divided by 2. Okay. So it's just some definition. Yeah. So this one is just about the definition of the graph. And we also have the degree of the vertex. Degree of the vertex is the number of the edge incident to it. Okay. And a tree is a special graph with no cycle, right? You remember for the tree, right? The tree is just the special graph, no cycle. Yeah. But for the graph, you may have the cycle. For example, this node may connect to this node. Okay. So for example, we also have something like undirected graph, meaning there is no direction between the two nodes. For example, A and B, they're the path, right? This means that you can traverse B from A, or you can traverse A from B. Okay, so there is no direction. Sometimes you also see that there's the weighted graph. It means that instead of just there is the connection or not, they also have the weight. For example, the weight from A to B is 7. The connection between A and B have the weight 7, for example. Okay, so it's just a number. Or the directed graph. Directed graph means that there's the direction in the connection. It means that, for example, in this one, there's the path from B to A, right? But it's not from A to B, not. Okay. So there they call it a directed graph. Okay. Or a complete graph. Complete graph means that one node connect to all the other nodes. Yeah. So they all connected each other. Okay. So it's just a terminology. Okay. So if the edge, right, X and Y, right, So they the X and Y, right? If they the undirected graph, right? Then E is incident of with X and Y, okay? And X is adjacent to Y and Y adjacent to X. It's just like adjacent to each other, okay? And E called the incident with X and Y, okay? And if E is unordered, then G is undirected. Unordered means that X and Y or Y and X have the same thing. You don't distinguish the X and Y or Y and X. But if you distinguish, right, the difference between X and Y and X, right, then G is called the directed graph. Here, for example, you have the X and Y mean that they're the one path between X and Y, right? But they no path between the Y and X, right? They know, right? If they are directed things, okay? And yeah, like mentioned, right? If E is XY is a directed graph, right? Then Y can be reached from X, but it may not vice versa, right? So X may not reach from Y, right? Because if they no path, then no way. Only one path from X to Y, but not from Y to X. Okay? So therefore, we can say that Y is the adjacent to X, but not vice versa. Because Y adjacent to X means that from X can go to Y, but they're not vice versa. Y doesn't mean like X is adjacent to Y because there's no path from Y to X. Okay. And a path, like consider, right, a path is just a sequence of the distinct vertices. For example, you have the path from A to B, B to C, C to D. Sorry, A, B, D first, and C. Okay, so you can have the path from A to C. Right? This is the A, B, D, C. Okay, and the cycle here, if you have the path back to the original node. For example, you have the A go to B, B go to D, D go to C, and C go to back to A. Okay, yeah, just like this. This is the path, right, from A to C. Okay, or if you have the cycle, then we have the cycle from A back to A. Okay. So in the path, right, you can see, right, if there's a path, then the number of the vertex, right, will be more than 1 compared to the number of the edges. For example, this one 3 edges, but 4 vertex. But in a cycle, then the number of the vertex is equal to the number of the edges, okay, because back to the original node. Okay. Then undirected graph consider the connected if there's a path from any vertex to any other vertex. Okay, it means that you have something, okay, so yeah, unconnected, right? Because from you can reach any node, right, in the graph, right? For example, this one you can reach from here, right? You can all reach, but this one is not the connected graph, right? Because this node, no way you can go to this node, right? So this graph is unconnected. But if you remove this one, then this one becomes the connected. Okay. And this one is for the undirected graph. But for the directed graph, right? Because we have the direction, right? So they call it a strongly connected if they are path from any vertex to any other vertex. For example, you have the A, B, and C. Okay. If we have this one, so this graph will be the strongly connected, right? Because, for example, for any pair, you can find a way to go to the for example, you want to go to A to C, right? You can go this way, right? Or you want to go to B, A to B, you can directly go here. So this is they call it a strongly connected one. But this one is not strongly connected. For example, A, B, C. So there is the path here, the path here. Why they are not strongly connected? Because you cannot find any way from C to A, right? From C to A. There's no way from C to A, right? So they are not the strongly connected one. Okay. The strongly connected one, if they apart from any vertex to any other vertex, they are strongly connected. Okay. Their graph is considered cyclic if contain one circle. Okay, that's easy. So for example, this one, they are cyclic because they are circle here. Or this is also the cyclic one because it's circle. Otherwise, they call it a cyclic. Okay, a cyclic. Okay. So a graph called a cyclic if they cycle. If they no cycle, they call it a cyclic. Okay. Then the complete graph. So the complete graph is like I mentioned, right? Complete graph means that just a simple undirected graph that contains exactly one edge between each pair of the distinct vertices. So they call the complete graph mean that each node, right, have only one connection, which on the other node. Yeah, one and only one. Yeah, which on the other node. It's just like you have four things, right? Four nodes. Then the completed graph is just connecting all the nodes together and only one. Yeah, right. So one node connect to one node will connect to the other three nodes. Yeah, they call it okay, complete graph. So for the application, right, actually the graph have a very huge application. You can see the graph everywhere. For example, if we look at the single SMRT map, right, we can consider the station is the vertex, and the route or the connection, the route between two nodes is the edge. Okay. Or in the chemical, right, chemical field, right, you can see that. For example, you can consider like the atom is a node and the bond is edge, or computer network, right? Then you can consider each computer is one node, and the connection between the computer, like the network between the computer, is the edge. Or in the electrical circuits, right? Then the electrical devices are the vertexes, right? And the link between the devices is just the edge. So there are many one. Yeah. So a strongly connected directed graph is also the cyclic graph. The strongly connected graph is also the cyclic graph. Cyclic graph. Strongly connected one. It means that every node can reach from the other node, right? Yeah, it will be the cyclic graph. Because you can reach A to B, you can also reach B to A, right? And because they are directed graph, so it should be have the cycle. Okay, so for the graph representation, how we can represent a graph? So very important, we have two ways. We call it adjacency matrix or the adjacency list. Okay, so this one you will be asked in the lab or in the assignment also. Okay. So how we represent a matrix, represent a graph using the adjacency matrix and the adjacency list. Okay. For the adjacency matrix, it's very simple. It's just an array, 2D array, with a size v times v. So if there's a connection, so we put the value of the matrix u and v equal 1. Otherwise, we put a 0. Okay. And you can see that if the graph is undirected, right, there's symmetrics, right, because the value of u and v should be equal 1, right? I mean the value because there's no direction, right? So the array value of the uv equal vu. But if the directed graph, they may not be symmetric. Okay, so okay, just for the illustration, right? For example, you have this graph. So for example, you can see, right, we have the trail node. So we create a trail times trail array. Okay. And then if there's a connection, for example, you look at the yellow one, 3, 7, right? Because there are 3, 7, if we not the connect, there's the half between 3 and 7. So we just put 3 and 7, 3 here, 7 here equal 1, and 7, 3 also equal 1. Right? If there's no connection like 7, 8, right? 7, 8, there's no connection, right? There's no connection between 7 and 8. Then you can see 7, 7, and 8. They are 0, right? And 8, 7 also 0. 8, 7 here. 8, 7 also 0. Yeah. 8, 7 also 0. And because it's the undirected graph, then you can see there are symmetric matrix, right? Matrix, right? Symmetric matrix. Because you can see they are quite symmetric, right? Yeah, symmetric by this line. Okay. So value here will be equal to value here. Value here will be equal to value here. Yeah, it's quite symmetric. Okay. So this is the way we represent the graph using the matrix. It's just very simple. It's just an array. And there a connection, then the value of uv will be equal 1 or vu equal 1. Okay. uv and vu equal 1. Otherwise, it becomes 0. Okay. Then the other ways we can represent a graph is using the adjacency list. Adjacency list is for each vertex, right? We use a linked list to link on the other vertices that connect to this node. Okay. So yeah, I mean, just go to one illustration, right? We have the same things, right? So for example, for the node 1, right? We just node 1 here. We just create a linked list to link on the node that connected to this node 1. For example, 1 connect to 2, 3, 4, 11. Then we put the linked list 2, 3, 4, 11. Okay. Or for example, 7, right? 7 they only connect to 3, so we just put a linked list with 1 element 3. Okay. So why the good and bad in these two representation methods? For the adjacency matrix, right? So if you want to check whether two nodes is connected or not, right? It will be constant time, right? Because you just access the array UV, right? To check whether UV is equal 1 or 0, say a constant time. But they are the pros, but the cons is the space. You need the V square, right? To store the matrix, right? And you see if the matrix, many of the elements is just 0, it means many H are not connected, right? Okay. But you still need the the V square, V number of vertex, right? V square to store the matrix. But the access time is constant. But for the adjacency list, right? It's very efficient in the space, right? Because you only need to use the array to keep the list of the vertex, and then for each one you keep the the connection, right? The edge. And the edge is just a number of the edge, right? It's 2 times of the edge, because if an undirected graph, so you store 2 ways. 3, for example, 3 connect to 7 and 7 connect to 3. So the complexity will be V, I mean the space will be V plus 2E, right? I mean the space, or it's just the O of V plus E, right? The space. Compared to the adjacency matrix, right? You need the V square. Okay. Then this one you save a lot of things, but the cost is the access time for UV is linear, because you need to traverse the linked list, right? It's not the instant time like the adjacency matrix, right? This one, if you want to check 2 connect to 6 or not, right? Then you need to traverse the linked list. So it's the linear time, it's not the constant time. Okay. And this is for the unweighted. Then how we represent the weighted graph? So very simple. Actually, the weighted graph is just similar like that. It's just that we just add the weight, right? So for the adjacency matrix, you can directly, I mean, instead of just like if they connection, then you put 1, right? Now you can just put the value of weight, okay? And if not, then you can put 0, yeah. Or you put any number like infinite number or whatever, yeah. So instead of just using the 0 or 1, now you just use the value of the weight instead of 1. This is for the adjacency matrix, okay? For the adjacency list, then we just need to add 1 more field in the data. For example, 1 connect to 2, right? Previously, we just put the linked list just have 1 field like 2, right? Now we just put 1 more field like contain the weight. Or for example, 2 connect to 3 and 4, right? With the weight 10 and 14. So we just create a linked list and we add 1 more entry in the linked list, like to represent the weight. So then we can represent the weighted graphs. Okay. So in a summary, right, we learn about the concept of the terminology of the graphs, like the directed, undirected graph, the cycle, the path, right? And then for the graph representation, we have 2 data structures to represent the graphs, adjacency matrix and adjacency list. And of course, each of them they have the pros and cons. For adjacency matrix, the space is bigger, it needs a V square, but the access time is constant, right? Just access the array. For the array of for the adjacency list, right? We save spaces. We only need the V plus E, right? Space to store it. But the cost is the access time is linear. It's not a constant because we need to traverse the linked list. Okay, so that's the the 2 ways to represent the graph. Okay, so I think that's all for today. So any question? There one question: does the order of each linked list connect to the vertex matter? Frankly speaking, the order doesn't matter. You can add in any order because the linked list is just so that okay, this is on the node that connect to this node. So in the lab or in the assignment, I mean the order doesn't important. You can add in any order. So when you create a linked list, right, to store the connection, you can store in any order. It doesn't matter. The next assignment, I will release by this weekend also, and will give you enough time to complete it. No worry. And the first assignment will not be so difficult. It's just about the hashing things. Okay, and you have enough time to do that. The graph. Wait. For the assignment, the first assignment, the graph I will combine with breadth-first search and depth-first search. Okay, so the graph will be in the second assignment. So for the first assignment, for the first assignment, there are only let me see. There may only 2 or 3 questions. Yeah. For the okay, so for the I mean, I will try to make the on assignment only about 2 or 3 questions for you. Of course, I try more easier question, but I will have one harder question for the, I mean, the one that want to challenge. I cannot make all the question easy. But I will try, for example, if 3 questions, then we will try to make it like 2 questions easy, and 1 is a challenging one. So that we, if the challenge, I mean, the good student or a challenge, they want to have a challenging question, had a good score, A score or something, then we need to do that. Okay. But there will be the easy one also, so that everyone can do at least 1 or 2 questions. Yeah, I will release the lab content and everything by this weekend. No worry. So that in the next week you can have the lab material. For the adjacent list, right? Just say 1 connect to 2, 3, and 3, 1. So either 3 the same linked list, not. What do you mean by the same linked list, not? So 3 is the not 3, right? So for example, 1 connect to 2 and 3. So 1 you will refer to 2, 2 will refer to 3, and then you have the new not 3 refer to 1. Yeah, link to 1. So of course 3 and 3 is the same, right? For the adjacency matrix, lab, the lab will have 3 questions. Okay. I will release very soon, 2 or 3. I will adjust it based on the things. For the adjacency matrix, can you elaborate on the struct? The E side and the adjacency matrix here. The E side and V side is just a V side means that the number of the vertex, and E the number of the edges in the matrix. Okay, and this one is, you know, right, just array. So we store the number of the we store the number of the vertexes and the number of the edges. I will release the template for that during the lab also. So there's the template for you. Then I will ask you to write just some function, for example, add it or something, traveling or something. But the template for the graph will be given in the lab or in the assignment. It will be given. Then you just fill in some function I ask. Okay. So you don't need to build from the scratch. So you have the template. For the graph, may I know the node hold the references for on the order node? They adjacent to the layer 3 or either just defined based on the adjacency matrix list. I mean, when we build the graph, right? Actually, the input is just which node connect to the order node. Yeah. So the input is just like that. For example, 1 connect to, for example, in this one, the input is just like 1, 2. It means that the connection between 1, 2, 1, 4, 1, 3, 1, 11, and then 2, 5 or something. Yeah. Then when we design the graph, right, we design whether we store it like the adjacency matrix or the adjacency list, so that we can do the process later. We cannot using this form, right? to process, right? Yeah, maybe. Yeah. In the lab, I will give you on the format. Then I ask you to do some function. For example, calculate the degree or something, right? Yeah, what the reason we use double pointer? Double pointer is just for easier. So that you can increase the size or something. You can use the exactly the array v size, right? Or you can use the adjacency. The double pointer. The same thing. When you double pointer is just for the flexible one, right? When you allocate the memory. They are on the same, right? When you do the processing, when you create the double pointer, when you call the element, you also do the same thing, right? Just call the adjacency matrix A, B or something. So they are the same, right? So double pointer is just good for you to like allocate the memory, or sometimes you want to release the memory. But the double pointer is just like can be processed like exactly like the array. Yeah. Explain the number of the node in the linked list for the adjacency list. Let me see. The number of the node in the linked list. What's that? The number of the node in the linked list for the adjacency list. Oh, okay. The number of the node right here. The number of the node you can see, right? We first need the number of the on the vertex, right? So they are V, okay? And the number of the node in the linked list, right? And how many nodes? So you can see, right? For example, for each edge, right? You will have 2 times for each node. Yeah. For each edge, right? You will have 2 times. For example, 1, 4, right? So in 1, you create 1 node entry 4, and from 4 you create another node entry to 1. So that's one for each edge. We need to have 2 definitions, right? 1 to 4, 4 to 1. So that's why the number of the node is 2 times. So that's why the space we need is V plus 2E. Okay? Because they are the undirected, right? Yeah, if the directed graph, then we only need 1. This one is for the undirected one. So if of course, if a directed graph, then we only need 1. Okay. Any more question? Yeah, just ask. If you don't have any question, you can leave. Otherwise, you can stay here to ask me. Does the order of the adjacency list matter? No, it not matter. You can put any order, because the adjacency list is just to show that okay, these not connect to the node we are interested in. So the order doesn't matter. Yes, the final question will be set by me. For the part 2 and the final test will be set by me. For the first part, it's set by Dr. Lo. So I'm not so sure how about that. But for the second one, I will set. It will be set by me. So for the lab, for the assignment 5, 6, 7, 8, and lab test 2 and the final quiz, I will set the question. Okay. So if nothing, then I think we can stop here. Let me stop the recording.